Hello! Let's look at Dijkstra's algorithm. The problem we'll be solving is finding the shortest path between two nodes in a graph. For example, in this graph we are tasked with finding the shortest path between node 0 and node 6. All edges in this graph are non-negative. This is an important prerequisite for this algorithm to work. As you can see, the shortest path can be quite convoluted sometimes, so we need a smart approach. Surprisingly, the problem becomes easier when we think about finding the shortest path to every node in the graph, which is what we will do with Dijkstra's algorithm, as opposed to just finding the shortest path to node number 6. Before we look at the algorithm, let's explain a simple term, relaxing an edge. In this example, we have an array where we assigned the smallest known distance to every node. However we did that. By relaxing, we will be trying to improve this array. When we relax an edge, we will check if we can improve the distance to node B or C by taking the path through node A. In this case, node B's distance started as 10, but if we assume that node A's distance to the origin is 2, then by taking the edge connecting them, we discover a better path to node B through node A. This path has a total distance of 5, the distance to get to A, plus 3, the weight of the edge. As a result, we update our smallest known distance to node B. Now moving on to node C. This time, we notice that we can't improve node C's distance, therefore we just do nothing. We have successfully relaxed all the edges that start from node A. Another thing to note is that if our goal is to find the shortest paths to B or C that start through node A, then we have to be certain that the distance we have assigned to node A is indeed the shortest one. If it turns out there's a distance to A that's smaller than the one we assigned, we would have to relax node A again to find the appropriate values for shortest paths to B and C in this example. With that out of the way, let's now look at how Dijkstra's algorithm actually works. It's very simple. It starts by setting each node's starting distance to the origin to infinity. In the array below, we chose to represent infinity as -1. The only exception is node 0, because that's the starting node, we set its distance to 0. After that, we try to relax every edge connecting node 0 with its neighbors. Then, we pick the node with the smallest distance that we didn't relax its edges yet. In this example, that's node number 2. And we repeat the process, relaxing its edges. We do that until we have relaxed the edges of every node. Now, let's go back to our original example. We have our graph and the distance array as we described. Additionally, we have a sorted array of pairs. Each pairs contain the number of a node and its distance. And we keep them sorted by smallest distance at the first index to largest distance at the last index. The purpose of this array is for us to know at any given moment which node is the one whose edges we should start relaxing. This is often implemented with a tree. It's not important for you right now to know the details. Just trust that we can insert, delete, and look for any element in that sorted array in O of log n time, where n is the number of elements inside it. It will remain sorted without us having to do anything. Our algorithm starts by setting the distance of the starting node to 0 in both arrays. Then we choose the first node in our sorted array. We remove it and we begin relaxing its edges. The distance of node 0 is 0, and the weight of the edge is 3. This gives us a smaller distance than the node 1's previously assigned distance, infinity. Therefore, we update our arrays with a new distance. The same is true for node 4. Once again, we update our arrays. Likewise with node 2. You will notice, in our sorted array, this pair was inserted before the previous two pairs. This is because this array remains sorted based on distance. Node 2 has a distance of 1, which is less than the other distances. Therefore, it's the first element in the sorted array, regardless of which order they were inserted. This is where things get interesting. Now that we have successfully relaxed node 0, Dijkstra's algorithm proudly declares that it has found the shortest path to the first node in the sorted array, node 2 in this case. Although we won't cover rigorous proof, it's important you understand, at least intuitively, why that's the case. Let's think about this. Would it be possible that we discover a better path to node 2 in the future? Any path to node 2 begins from node 0. A hypothetical better path to node 2 would take one of these red paths to node 1 or 4, but these paths are already longer than the green path to node 2, and since every edge is non-negative, a path starting from those ones would be at least as long as these red paths. This wouldn't be the case if we introduce this mysterious purple edge with negative weight. Now the shortest path to node 2 is the one through node 4. As you could probably guess, Dijkstra's algorithm is not suitable with graphs with negative edges. Back to reality. Now that we have asserted the shortest path to node 2, it's time to remove it from our sorted array and relax its edges. We can't improve the distance to node 4, but we can improve the distance to node 5. So we update our data accordingly. Upon relaxing node 2's edges, we move on to the next node on the front of our array, node 1. Once again, we proudly declare that we have found the shortest path to node 1, as any other path to node 1 we didn't account for would have to start with one of these red ones, but they are already bigger or equally big than the path to node 1 that we have found previously, because they are further to the right in our sorted array. We remove it from our sorted array and begin relaxing its edges. We notice we can improve the distance to node 3, so we do. Then we look at node 4, can't improve the path this time, and with that we are done with node 1. So we move on with the next node in our sorted array, node 5. Once again, we can be sure that the shortest path to node 5 has been found, and we will now relax its edges. We remove it from our sorted array. The new distance to node 4 is the distance to node 5, being 3, plus the weight of the edge, 2. This totals 5, which is smaller than its previous distance, 6. And we update our data accordingly. The same is true for node 6. And the next node we will relax is node 4 for the same reasons. We remove it from our sorted array, and we try to relax its edge to node 6. The new path has a weight of 7, which is smaller than a 9, and we update our data. Then we try to relax its edge to node 5. There's no improvement, which is expected because we have already found the shortest path to node 5. The next in line is node 3. We remove it from our sorted array, and we relax its edge to node 6. The final node in our sorted array is node 6. We remove it from our set, and with no edges for node 6 to relax, we move on to the next one in our sorted array of pairs. The algorithm notices that it's empty and terminates successfully, giving us the shortest path from node 0 to every other node in our graph, including node 6, our initial objective. The time complexity of Dijkstra's algorithm is O of n plus m log n, where n is the number of nodes in the graph and m is the number of edges. As you would expect, this log n comes from our sorted array implementation that we took for granted. With that, you have successfully navigated Dijkstra's algorithm.